In today's video, we're going to understand one of the most important concepts in structural and mechanical engineering, which is shear force and bending moment diagrams. We will learn what shear force and bending moment actually mean, why they occur in beams, and how to draw SFD and BMD step by step for different loading conditions. By the end of the session, you will be able to analyze any beam with confidence. So let's get started. Consider an overhead crane with two lifting points. The crane girder is supported at both ends. One hook applies a load at 2 meters from the left support, and the second hook applies another load at 2 meters from the right support. Distance between two lifting point is 3 meters. To analyze the system, let us treat the girder as a simply supported beam and draw its free body diagram. The beam is horizontal, supported at both ends, and subjected to 2-point loads applied at the specified positions. Before going further, please subscribe our channel. It motivates us to make more videos. Now, let us see that how the stresses occurs in the beam subjected to this loading. Also how the shear force and bending moment diagram are important. Each applied load can be resolved into two internal effects within the beam. The component parallel to the beam's cross-section produces shear force. If we consider the neutral axis located at the centroid of the cross-section, then applied forces results in the upper fibers of the beam going into compression, and the lower fibers going into tension. These internal forces are equal in magnitude and opposite in direction about the neutral axis. They do not create a net force, but together they produce a couple, which is known as the bending moment. Drawing shear force and bending moment diagram is just a graphical representation of these load at each location of the beam. The shear forces and bending moments along a beam do not depend on the geometry of the beam cross-section or the material. They depend on two factors only. Number 1, how the beam is loaded. Number 2, how the beam is supported. Let's look at loads first. The most common ways of applying loads to a beam are concentrated forces, distributed forces, and concentrated moments. In the real world, beams can be supported in many different ways, but for analysis purposes, supports can be modeled as one of three idealized supports: pin supports, roller supports, and fixed supports. Each of these supports restrains the beam in different ways. Pin support allows rotation, hence, it has only reaction forces, which are horizontal reaction and vertical reaction. Roller support allows rotation, as well as horizontal movement, hence, roller support has only one, vertical reaction. Fixed support do not allows any rotation or movement, hence, it has horizontal reaction, vertical reaction, and moment reaction. Let us see how to draw shear force and bending moment diagrams with one real-world example, as we stated earlier. Consider an overhead crane with two lifting points. The crane girder is supported at both ends. One hook is located 2 meters from the left end, and the other is positioned 2 meters from the right end. If we analyze only the horizontal beam, it can be treated as a simply supported beam, with 2-point loads 100 kilograms and 200 kilograms, applied at the specified locations. This is isolated beam with loadings and supports. First step is to draw free body diagram. A free body diagram is a simple sketch that shows all of the external loads acting on a beam, and any reaction forces from supports. Figuring out the free body diagram is an important first step in determining the shear force and bending moment diagrams. Let's start drawing the free body diagram. First, draw a horizontal line showing the beam length. The beam is simply supported at both ends, A and D. Let us consider horizontal and vertical reactions at support A, RHA, and RA, respectively. Vertical reactions at support D is RD. Point load F1 equals to 981 Newton, acts at point B, which is 2 meter away from left end, and point load F2 equals to 1962 Newton, acts at point C, which is 2 meter away from right end. Distance between two loads F1 and F2 is 3 meter. This is complete free body diagram. Before going further, let's consider sign conventions. Applied forces are positive if they are acting in the downwards direction. A shear force, which tends to rotate the beam in anti-clockwise direction, is negative, and if shear force, which tends to rotate the beam in clockwise direction, is positive. Now, second step is to find out the reaction forces HA, RA, and RD, and/or moments at support's location. This can be calculated by three equilibrium equations. These equations state that the sum of the forces in the horizontal direction equals to 0. The sum of the forces in the vertical direction equals to 0. And the sum of the moments taken about any point must be equal to 0. Let's apply second step in our example. The sum of the forces in the horizontal direction must be 0. HA is the only force in the horizontal direction, so it must be equal to 0. Sigma Fx equals to 0. Hence, HA equals to 0. The sum of the forces in the vertical direction must be equal to 0. So RA plus RB equal to 981 plus 1962. Hence, RA plus RB equal to 2943. We will keep this equation as it is. Now, the sum of the moments about any point must be equal to 0. If we choose to take the moments about point D, then RA multiplied by 7 minus 981 multiplied by 5 minus 1962 multiplied by 2 equal to 0. So, RA can be calculated as 1261 Newton. Put RA in the previous equation. So, 1261 plus RB equal to 2943. Therefore, RB equal to 1682 Newton. All of the external loads acting on the beam have now been determined, and the free body diagram can be updated. Now we can start to draw the shear force and bending moment diagrams, starting from the left side of the beam. We can draw the free body diagram, showing a beam segment, which has been cut, immediately the right of the point A. To maintain equilibrium, the shear force, Vx, must balance the 1261 Newton reaction force. Similarly, the bending moment must balance the moment generated by the 1261 Newton reaction load. So the reaction force at the cut plane, Vx, is equal to 1261 Newton, and reaction moment is equal to 1261 multiplied by x. Let's draw shear force and bending moment diagram. First draw a FBD, which we have already drawn. Below it, draw two horizontal lines, along beam length, for shear force, and bending moment. Now, Vx is equal to 1261 Newton positive. So, draw vertical line, at point A, and complete it till point B as it is constant till point B. Now, moment equation is 1261 multiplied by x. This is straight line equation. If we put x is equal to 2 meter for point B, then it comes 2522 Newton meter. We can draw straight line till point B, showing 2522 Newton meter. The process is then repeated, moving the location of the imaginary cut further to the right. This time, the cut is placed immediately after the 981 Newton force, and the free body diagram is drawn. The shear force and bending moment can be calculated by applying the equilibrium equations. So, the shear force at cut plane is equal to 981 minus 1261 is equal to minus 280 Newton. And bending moment is equal to 1261 multiplied by x minus 981 multiplied by x minus 2, which comes 280 multiplied by x plus 1962. Further, we'll update our shear force and bending moment diagram. This time, the shear force is negative 280 Newton. Hence, draw the line in negative direction and complete it till point C. Also calculate the moment, by putting the x is equal to 5 meter and complete it in the bending moment diagram. The process is then repeated, moving the location of the imaginary cut further to the right. Now, the cut is placed immediately after the 1962 Newton force, and the free body diagram is drawn. The shear force and bending moment can be calculated by applying the equilibrium equations. So, the shear force at cut plane is equal to 981 minus 1261 minus 1962 is equal to minus 1682 Newton. And bending moment can be calculated same way as earlier, so it comes minus 1682 multiplied by x plus 11772. Further, we'll complete our shear force and bending moment diagram. So, this is the complete shear force and bending moment diagram. Let us know in comment section, did you like our video or not? Thank you for watching the video.